So today we are going to talk about problem solving. We will continue with the reasoning. We have to finish deductive reasoning and inductive reasoning. We'll continue next week. It's okay to stop in the middle. And May suggested that I cover problem solving now because that's your current Gaddafi, and I think it was a great idea. So I will present you the main definitions, the traditional way that problem solving is defined. But as most textbooks, I find these definitions and oversimplistic and even sometimes confusing. So on the way, I will raise questions and challenge some of them. Okay, why is it not working? So problem solving is usually defined through two alternative strategies: convergent thinking and divergent thinking. So we will mostly talk about convergent thinking because most of the theoretical mess with and most of the research was based on well-defined problems. We will understand it soon. So convergent thinking is when we have a well-defined problem, meaning that we think that we know that we have a problem. We think that we know what is the question, and we feel that we know what are the alternative ways to solve the problem, what are the tools at our disposal, and we perceive the range of optional optimal solutions. They are clear to us. And that's in contrast to divergent thinking, where we usually apply in ill-defined problems, when we don't know sometimes whether we have a problem and what is the problem and what kind of solution would be best. In divergent thinking, it's usually connected to creativity, which we'll, if we have time, we'll talk about it on Thursday. And when I say what we think that we know, it's not because I think that we don't know, but we never know that we know what we think we know. And we'll see examples. All right. So convergent thinking, we gather the current information presented, we round up all information, what we perceive as pertinent information from memory. We clearly identify the elements in play, the connections between those elements along time, and everything converges towards a clear expected solution or a number of solutions. So the obvious example would be a multiple choice question where you have to find one of the 4 or 5 alternative answers. So here in this diagram, all the pertinent information and everything converges towards the answer. Divergent thinking, it goes anywhere. It diverges to any direction that we find ourselves choosing. So defining the question is always the big thing. It's the most difficult part, it's the most important part. It could be claimed maybe that most of the significant developments in science are in fact, could be defined, could be described as a redefinition of the question. So one example is some lectures ago, I talked about attention and memory, and I offer, not that I'm just using it as an example that we talked about, not because I think that what I suggested is of any, I think it's, or personally think it's of value, but in that example, we could reappraise all or most of the research, the empirical evidence we have about research in attention, that since William James have been defined as what we see, we have to understand attentional processes, the effects we observe in the lab. We try to define, to understand them as a solution to the problem of limited capacity. So if, as I suggested then, we redefine as a problem of access to that information and not limitation, suddenly a whole new endless world is possible. All right. So we have the present state, which is clear, the obstacles are clear, and the goal state is clear. And we try to either remove the obstacle or avoid it or circumvent it. And the terminology used is we navigate the problem space. The problem space is everything that is pertinent to the, is it working? Sorry, that is pertinent to the problem, which again, everything is clear and defined. So it includes time, it includes space that can be physical or not. So games are obvious examples, all kinds of chess, Go, what's the name of that one? The only that you jump, checkers, etc. We'll see it later. So we'll begin with the perhaps the most important. Sorry, just a second. I have something is going on here. You can hear me, see me. Everything is okay. Anyone? Can you hear me?
Yep.
Yes? Okay. So Thorndike was a very important person, mostly in the field of learning. I think probably the most influential psychologist in everything concerning education, educational psychology, child education and learning. Most of his career he spent at MIT, Massachusetts. He was the president of the American Psychology Association from 1912. And apparently he's the 9th most cited psychologist of the 20th century. So what we'll see now is part of his PhD dissertation, which was called Animal Intelligence. And he came up with the law of, well, I'll tell you. So these are called the puzzle boxes.
But how is a new skill learned? That was a question which began to fascinate Thorndike. To answer it, he built some ingenious puzzle boxes from which cats could only escape by operating latches. And in you go. The cat appears to be very clever in engineering its escape, solving the problem with a deftly placed paw and a push of its nose.
So this latch, there is a rope inside, and
Thorndike didn't believe that an animal, even a clever cat, understands the consequences of its behavior. When he placed a cat in the puzzle box for the first time, Thorndike was unable to see any evidence of flashes of insight. The successful actions appeared first by chance. He proved that the apparent cleverness arose by trial and error, and used graphs to measure the rate of learning. A well-practiced cat quickly recalls the actions that help it escape to its reward of food. If an action brings a reward, Thorndike believed that that action becomes stamped into the mind. In his thesis, he explained further his ideas about learning, that behavior changes because of its consequences. He called this his law of effect, which explained how even wild creatures develop new habits.
Well, so it's funny now. I haven't thought using cats to understand anything is funny. This is the most crazy, ununderstandable, complex entity. All of you that know cats, like nothing in cats makes sense. And certainly not simple. Anyways, so the law of effect, so what he found is that repeated when the cat was caged again and again in the same context, a long time. Obviously, it took shorter and shorter time for the cat to escape, which means that the cat learned something. So the cat, what he observed is that the cat initially tried random actions, and by trial and error, and achieved success accidentally. And improvement was by associating the circumstances from the current situation to its memory, to information. So Skinner compared that to, he called it evolution applied to behavior, meaning that the cat brought random options, and then the situation selected the solution. So what from those observations we could raise the hypothesis that what would determine the rate of learning of the cat would be the time lapse between the trials, between the experiment, if it was in the same day, one after the other, or between trials a month, probably the cat would not connect. And second, the similarity of the circumstances. If it's the same cage, maybe the same hour of the day, maybe connected to, yes, please feel free not only to ask questions, to interrupt me. Okay.
Professor?
Yes, Maya?
Yeah, I was thinking that what the researchers said at the end of the video, that behavior is created by consequences, isn't that a lot like earlier thinking in psychology, that causation is like creates behavior, like like they said that children would behave a certain way because they were punished, and so they associated like some kind of behavior as bad because they were punished, so they like saw the results, so that like behavior is always about consequences. But hasn't that like changed a lot now, or is this like not all the same thing,
Isn't that what?
or is it not at all the same thing that he was talking about?
No, it is. Is operant conditioning, like connecting between events. This is, and you raised causality. We'll talk about causality next week probably. So in my personal opinion, what changed between then and now are only terminology, narratives, and the story became more rich and complex. But I don't think that anyone until today would claim that the connection between sequential events in time and the application of the prediction of the perceived sequence of events is not connected to behavior. I think that from amoebas to us and babies, and we talked about it, but we'll talk more, it's still the same story, and it makes sense, right? So so you just raised that today we don't see like that. Maybe it's only in terms of terminology and more complex stories. Did I answer your question, Maya?
Yeah, completely. Thank you.
Okay. And that's exactly what you asked. Well, we could assume, and actually it has been shown, that the more similar, not the time lapse between the events, obviously, which is memory, right? And the similarity of the circumstances. The more similar it looks like, so the more the memory or the abstraction or whatever is accessed is the better, the faster the connection to that piece of memory. So this kind of problem solving has been traditionally defined as problem solving without insights, which I find a little bit. I'll talk about it soon. So trial and error problem solving. So improvement is gradual. There is no understanding about the solution. The solution is preceded by furious action, observable action, random action, like the cat tries everything. And the solution is accidental. Okay. The second way to solve problems, according to the textbook's definitions, are insight-based problem solving. So here I'll show you another classical video with a monkey. It's not in what you'll see, but imagine that in the beginning, the monkey observed the problem and thought. It looked like the monkey was meditated, and then it was like eureka, and the monkey, the chimpanzee, found the solution. So this guy is fixing this tube with liquid inside and a peanut inside. The monkey never saw it. This is not the monkey was not trained. So this is after the monkey already meditated and thought. It went and brought water inside its mouth and raised the level of the water inside the tube until it could pick it up. So the monkey explored in the beginning what was not here in the video. The monkey explored mentally, abstractly the problem space, and then it had an insight and applied it. So improvement is sudden after the Eureka solution. And it's assumed that the monkey understood what it was doing. There was no action, like it was abstract problem solving. And it was based on analogies, meaning that the monkey connected the fact that it observed in the past peanuts floating on liquid, and that it could bring water from a bucket and then solve the problem. Now, this is an interesting paper. It's inside the resources. Give a look. It's really nice. It's from Cambridge and the University of Auckland in New Zealand, 2014. So our results indicate that New Caledonian crows possess sophisticated, incomplete understanding causal properties and displays, rivaling those of 5 to 7 years old children. Now, in Israel, there are a lot of crows, and they are crazy intelligent. Crows are, it's unbelievable. Anyways, so it's based on the Aesop's parable, the crow and the pitcher. There is a story, I don't know, it doesn't matter. So the subjects were 6 wild North Caledonian crows. They were caught and housed in a cage. Two crows were not motivated enough, apparently, they told her. I find it funny, the lack of motivation. And afterwards, they were released. So these were wild birds. They were not trained or anything, okay? So the general procedure, they only habituated the crows to what you'll see soon. So water-filled tubes and a cube of meat and the other objects that you'll see soon, they were only habituated, they were not trained. They were given 20 trials. There were 6 tasks, 20 trials each. Okay. So the 6 tasks were like this. There is the first one, there is a tube full of a liquid with a piece of meat floating and stones, gravel. The other one, the same, but instead of a liquid, there was sand. The second one with liquid and the meat. And there were 2 kinds of objects. They were identical in color and size, but one was, how do you call it? It floats, okay? It's lighter than water. The other one was heavier than water. In the third case, the same tube with liquid, the 2 similar objects, one was solid, the other one was hollow. So this one had more volume. The fourth one was the same objects, but here there was much more liquid. The fifth one was these two tubes again, but the meat in the small tube was further away from the reachable height of the tube. And the last one, these two tubes, one of them, the blue one, was connected under the surface, so the crow could not see this connection. So when stones were dropped inside the blue one, the water level in the central tube where the meat was would rise, while in the red tube it would not. So let's see what they did. These little rings in its feet were added during the experiment, obviously. I don't know if they took it off after when they released. But these are wild crows, like they just arrived here. And these are among the motivated ones. So this is the heavier than water, and the lighter than water. And they look the same. Isn't it incredible? It didn't even try this one. Look, it tried. No, this doesn't. It floats. I find it crazy. Even for a 7-year-old child, I would think. Yeah, they didn't do well in this task. In average, I mean. I'll show you the results soon. I know it was this one they didn't do well. They didn't understand that going to the other one would be faster. And this one, here the water rises. So I said the opposite. So the blue, okay, apparently, yes, it was random. Sometimes it was the blue. So you see here, the blue, the water doesn't rise. So it has to go to the other one, to the green one or red one, I don't know. Incredible. No? Okay, so these are the results. These are the mean correct responses. So this would be chance level. I think chance level, if there was only two options. So they didn't do well in the volume one. They did do well in the further away one, and in the tube it was not significant. But look, volume, weight, This one, 90%. Okay, so let's look at the definitions of what is insight-based human intelligent problem solving. So first of all, what does understanding mean? Understanding is critical for having insight, like in the case of the chimpanzee. Obviously, the crows and Stoffel, they more than belong to the insight column, right? But what does understanding mean? So did the crows understand volume and weight? We don't know, and that brings us back to the metaphor, to the question about, does the physician fully understand when it correctly prescribes a medication? And we said that only biologists and the chemists and the physicists so understand. It can only predict. So if predicting is the criterion, so obviously all these animals predicted, but then also the cat could predict that pulling that rope would open the box. Fact is that it learned. So understanding is measured by explaining, declarative memory, if we want to talk about. So it's already meaningless, the word understanding, for this definition. Furious action. What is furious action? Observable action? Okay, so we see the cat doing all kinds of things, and then, but the monkey thinking, or the crowd thinking, or even us when we try to solve a problem, this is maybe not observable physical action, but inside the head it's still action. It takes time, and so the separation between physical observable action and not observable action, and how do we know that, or how do we know? I don't know, even from introspection. No, wait. So it's defined as the cat started to do all kinds of random actions, but the cat didn't try to groom itself. It didn't try to, I don't know, urinate. It tried things that from the cat's pool of possible pertinent options from its memory were relevant. It tried to meow, hello, I'm here, open. It tried to do with the hand. These are not random. And if those are random by the same, from that criterion, when we try to solve a problem and we raise in our head representations and ideas, I can do like that, I can do like, isn't it also random, or random within representations that feel that maybe, isn't it trial and error? Maybe I'll try like this, trial and accidental success from the options raised. The idea of analogies that we'll see soon, that insight-based problem solving is based on analogies and associations. It's memory. So the cat also brought from its memory of previous situations it was caged, or previous situations, again, that it was in a physical constrained space, and it tried what was, it did make analogies. So what I mean to say is that the separation, the definition between these two styles of problem solving, trial and error, that is ascribed to animals, and insight-based problem solving that is ascribed to humans. We are so smart. These are not really, these are not qualitative differences. They are quantitative differences. For instance, the more dissimilar is the current situation from whatever we have in our memory, the more difficult it will be to raise an analogy that is relevant. It can be the color of the cage. It can be with more extremely complex problem-solving cases, and we'll see an example soon. So there is a movie here. I will not show you another one. These are monkeys. It's a very old movie. It's impressive how the monkeys, they work together and they bring boxes and they bring sticks and they work together to catch the bananas. Okay, so what are well-defined problems? We already said everything is clear. The tools, the goals, the problem, and time, everything is defined. So most research has been done on well-defined problems. And a very famous one is the Tower of Hanoi problem. The two-string problem. I'll show the tumor problem. I'll show you later. But let's begin first with this question. Okay, it's for you. Try to solve it. So this is an example of how we use analogies and representations, abstract representations. The question here is, we know, given the radius of this circle, what is the length of x? Anyone can see it? Anyone can try? We want to know this length in comparison to the radius of the circle. Anyone can solve it? No?
Don't you use like Pythagoras theorem or something like that?
You don't have to. You don't have to. Try to move this without mathematics. Equal to R. Why, Jamaica? Can you explain why?
Because if you like move the triangle, it will equal R.
Yes, yes. It's if you flip it, this distance. Let me show you. This distance. This is a rectangle. So in a rectangle, the diagonals are identical. So the representation here, what the calculation, the critical insight was to move or to flip this triangle inside your head. But wasn't it trial and error? Like, didn't you raise all kinds of, I'll try like this, and then suddenly, oops, it worked. An insight. But this insight, is it different from what the cat did? Another one. So here you have to move only 3 balls, so the triangle will point down. You can move only 3 balls. No? Okay, I'll show you. So if you move these two balls here, you can see, suddenly you have the triangle. So what is the redefinition of the problem here is that imagining that the point is here. It's opening the possibility outside the space of the triangle. Okay? This one is more clear. So what you have to do is you can open and close only 3 links. Okay? And then you have to build one closed chain. You have 4 segments. You have to make one closed chain like a bracelet. But you can only open and close 3 links. No one? Am I wasting our time? Are you trying? You want more time? You want to try it, or you're waiting for me to give the answer? Oh, I miss live classes where I can throw stuff.
I think I know how to do it. Maybe.
Yes. Taylor.
So if you're looking at the top left one, if you unclipped like one of those rings and connected it to the next one.
Yes. So you connected.
And then you did the same thing with the other 2, if that makes sense.
So this is 1, you have 1 of 6, and you do it again, you have 2 of 6. You have 1 more to open and close.
And then the 2 like in the middle. Couldn't you just do like 1? This is so hard to explain without like being able to point.
So you're saying here 1, here 2, here 3?
Yes.
But then you have to close this one too. It
Oh,
has
you
to
have like a
bracelet.
full circle.
Yeah.
Oh.
A closed one, like a bracelet.
Oh no. Okay, then I am stumped. Stumped.
Chelsea May, tell me you know the answer so you won't feel stressed that you don't. You already knew it.
I actually never have seen this before.
You haven't?
Nope.
And you already know the answer, but you want the students to come with that.
Yeah, of course, that's it.
That's why you're not saying May the same, obviously. Okay, so here it's possible only if you, in your mind, redefined what is a segment. Because all of you are probably trying many options while maintaining the representation of 4 segments in your head. But if you take one segment and redefine it as 3 separate bridges, you solve the problem. Yes? Clear? Annoying? All right. Let's move to real life problems. So this is part of a study, a famous one. So participants were presented with two problems. This is the first one. This is a real life problem. This is, nowadays it was solved. But the idea, so a patient has a malign tumor in the stomach. It could be in the brain also, the same problem. It's impossible to operate, but unless the tumor is removed, the patient will die. So there is a kind of radiation that can be used to destroy the tumor. If the rays are directed at the tumor at a sufficiently high intensity, the tumor will be destroyed. But the problem is that this minimum threshold, this minimum high intensity, would destroy everything on the way. And in the case of, it depends where in the stomach, that would be fatally problematic. In the brain, as you can imagine, if it's in the middle of the brain, let's say, same problem. At lower intensities, the rays are harmless, but they will not affect the tumor efficiently. So how can we solve this problem? It is solvable. It's called the gamma knife problem. I'll give you a hint. The rays they are additive. So, all right, I'll jump to show you the continuation of this experiment. The second story they were told is about the Battle of Gettysburg in 1863. So the story is that there was a important area, a fort. I don't know if it was a fortress, but all the roads leading to that fortress, in order to conquer that fortress, you needed a minimum amount of soldiers, of contingent. The problem is that all the roads were mined, were booby-trapped. And you could not, there was no road through which you could pass with an entire army. It was booby-trapped in a way that only soldiers one by one could pass by. And you had a problem of time. Imagine it's like water through hoses. So if you need a lot of water passing through in a given period of time, you either could use a wide hose or many narrow hoses, meaning that the solution was, it was not a fort like this in Gettysburg. So the solution was to divide the contingent, the entire attacking army, into small companies that could pass through the booby trap at the same time and arrive to the battlefield at the same time. So that's the same solution for the gamma knife problem, that you, instead of one strong ray directed to the area, and that's the way it's done today, you apply a lot of low intensity convergent rays that they only at the site of the tumor. So everything on the way is not damaged, all right? So this is, as you can understand, it's the same solution. The interesting thing is like this. All right, so you can see here the problems are the same and the solution is the same. The interesting thing is that all participants heard both problems, like the first problem, the gamma knife problem, and then they heard the Gettysburg problem with its solution, and then they were asked to solve the gamma problem. Now, half of the participants the only difference between the two conditions is that half of the participants were explicitly told that the Gettysburg solution is relevant for solving the gamma problem. And the others were not explicitly told that. We are talking about 3 words. This solution is relevant for the other one. Now look at the difference. Those that heard, more than 90-something% solved the gamma problem. And those that were not told simply could not even, most of the, only 20% could even think about the possibility that there is any connection between them. So this is called the analogical paradox. I don't know why the word paradox sounds funny, but it shows that analogy from an abstract solution to another is the main process that we use to solve problems. So metaphors are analogies. And metaphors are stories that are easy to comprehend from our experience, in which we understand the elements and the connections and the relationships, or the causal relationships between the elements, and we can make the analogy to whatever we are trying to understand through the metaphor. And the problem with metaphors is that we never know. I talked about it in the first, in our second lecture, I think. The problem with metaphors is that you never know which parts of the metaphor are relevant and which parts are not. And sometimes, because the metaphor only works if it's an entire coherent story, we sometimes use some parts of the metaphor story to the new problem. And many times it's not relevant. So metaphors are dangerous. Algebra, so this is another interesting experiment. So participants were asked to solve algebraic problems. If you spend some minutes, you will remember. If you haven't worked with math since your high school, these are solvable problems that you will slowly try, and you remember, you know that you can do, and you play a little bit, you remember how that factor, okay. And participants were asked during the time until solution, they were asked to assess how they feel they are progressing, if they are getting close to the solution. And we can see that in algebra problem, even when they are still far away from the solution, they feel that they are progressing, they are getting closer. In insight problems, you don't feel it. You feel that, and that suddenly the insight comes. But there is a small, this is usually used to exemplify the difference between trial and error and insight problems, or other kinds of analytical problems, that the solution comes suddenly. But there is a small, I think, a question here, a methodological, because even for students that don't know math, that don't remember math, they know that they knew, and they know that there are a set of rules that they just have to remember, and they know it's doable. They know they will reach the solution. In insight problems, you don't know. And you know also that in algebraic problems, which are not considered based on analogy and insight, but you know that you get there. So maybe the question of how do you feel about your progress is confounded with measures of confidence. But in the textbook, you will find this as an example of why this sudden eureka moment in insight problems. Okay, so how do we solve problems? We know there is a goal, it's clear, we have the current state, the way things are now, and actions and operators, everything is clear. The heuristic meaning the internal cognitive process, the internal procedures or methods that we use, the heuristic is to navigate through the problem space, which is clear. So training makes a difference. For insight problems, the more you are trained in solving this kind of problems, the more you can consciously come up with analogies and change the representations, like in the example of the chain. If I would give you another riddle that you would have to change the representation of one of the parts, maybe you, even probably, you would come up with the solution because it's a meta-analogy. You learn that you have to change the abstract representations of how you perceive things in order to solve. Now, all these examples, real life examples, so you have your goal, you know what's the problem, the conditions, and potential actions that you can take. Now, one thing that I think it's very important is the fact that potential actions are not objective, they are subjective. By the same way that the cat didn't try to lick its fur because it didn't perceive it, consciously, unconsciously, it doesn't matter, as a potential action, as not part of the problem space, all our problem solving is constrained by what we perceived as possible or relevant actions, which are obviously, usually in real life, not clear. And I don't know how many of you have experience in coding. I do, I told you I like it. And many people like it. So you really feel it. You really feel these navigating, these even random, this exploration of, sometimes you see mechanisms in your brain, and you play with that. And I'm not talking about geometrical forms. It's hard to explain. So, as I said before, this is another example. The Tower of Hanoi, most of the research was based on games because they are well-defined problems. So Simon, the second author here, he received the Nobel Prize. So let's talk. How much time? Oh, 5 minutes. Okay. So the Tower of Hanoi. What you have to do. This is a classical game, and what's interesting here is that we can visualize in one slide the entire problem space. So what you have to do here is like this. There are 3 rules. 1, you can move only one disk at a time. 2, you can move only the disk on the top. 3, you cannot put a larger disk on top of a smaller disk. You can jump pegs. You can move this one to this one or to this one, okay? And the goal is to arrive to this situation with as fewer steps as possible. So this is the entire problem space visualized. So this is the only solution in 8 steps. So you can do mistakes and correct at certain points, but then you finish with more than 8 steps. Now, people usually make a mistake at this point. Why? Because here you have to move this small one back in order to move the middle one here. And participants, this has a feeling of going backwards, of not progressing. Now, experienced players like chess players, professional ones for sure, they can easily visualize the entire problem space in their heads, much more than that. But most people, we mortals, we cannot. So what do? We divide into sub-goals, meaning that we find the smallest problem space that we can visualize. So we find the biggest difference between where we want to achieve. And we select, we appraise the possible actions. If we cannot visualize the entire space to that goal, we divide it into smaller sub-goals until we reach the smaller sub-goal that we can visualize all the options. We do it in real life as well. So you have to, the goal is you have to take the children to school, and you have to cover the certain difference. You can use the car, and then the car obstacle, the car doesn't start, and then you have a sub-goal, a new battery, mechanic, sub-goal, etc., etc. I have to call, etc. Okay, so at the first glance, you may feel, no, this is not exactly the same, because here we have an expected obstacle. The car doesn't start. And in this game, you don't have this kind of surprise. That's not true, because you don't have, when you start to navigate through it, if you're not a chess player that can upfront visualize everything, you reach obstacles that you couldn't visualize. So they are as unexpected as in the case of the car is not starting. The fact that the experimenter knew upfront all the obstacles in a well-defined game the perception and the process of problem solving of the participant is the same. Okay? And this is why, I don't know if you know it, there is a rule of thumb in project planning when you plan time. So you have an initial estimation. Okay, I have this assignment. It will take me 2 days. I have to, then imagine, I have to read the material. I have to do like this. I have to do that right. And then, okay, 2 days. So the rule of the thumb is that whatever is the initial estimation, you double the number of time that you assessed. So from 2 days to 4 days. And then you move the 4 to the next large unit of time. So from days to weeks. So if you initially estimated 2 days, it will take you 4 weeks. If you initially estimated 2 weeks, it will take you 4 months. And it works. Obviously, the more experienced you are in exactly the same project, you have you can minimize this distance. But why does it happen? Because we cannot visualize from the entire problem space. We don't have the resolution. We have to divide it into small sub-goals. And we cannot visualize the inner things that can happen on the way. Okay? This is another example. In the case of, so nowadays with the AI, with the artificial intelligence, with neural networks, there are systems that can win any chess player or Go player. The thing is that those neural networks, however they learn, it was constrained by the observations they were given. That's why we need so much data, so much observations to feed the system. But it's constrained to whatever you feed it. So all the examples that a chess machine learning system was fed with were real games between real players. So how come that the real players, the best ones, cannot win the machine that is constrained by the games that those players did? So the problem is that players are, even the best ones, they are constrained by even small sub-goals, by heuristics. For instance, dominating the center field of the game. But dominating the center field of the chess game is a tactic to achieve the end goal to win the game. And this is a limitation, even emotional, maybe heuristic of the players. The machine, the AI system doesn't care. It doesn't see. It's not constrained by tactics. It has only one strategy. It can lose all its players if it calculated that by the end with 2 pawns it can win the game. So it confuses the heuristics of, and when real players win those machines is when they come up with unseen new tactics, like crazy stuff that until today nobody thought using because it doesn't make sense. But when they try this new tactics sometimes it's outside the space, the problem space that was fed to the AI system. Okay, next time we'll talk about ill-defined problems. We are done. Questions?